So right now I'm using stack memory for everything, but I actually need to use heap memory. And I'm gonna show you why. So let's start with looking at what the stack does. So say I have a program. Let's create a function that has a buffer. So function, and it has a buffer. Let's fill it with like 100k of bytes, 100k of characters. Might be easier if I just change this into kilobytes, just so that it's clear. Yeah, so I'm gonna fill this buffer with 100 kilobytes of characters. And this is on the stack. And stack memory is local to the function. So it gets created whenever the function gets called, and then it gets released whenever the function is done. And the nice thing about that is you don't need any kind of manual memory management. The code for this is generated by the compiler. It all is taken care of. So let's see how that works. Well, actually, to see how this works, I'm gonna need to have some way of seeing how much memory is allocated for my program. And unfortunately, there is no, I don't want to change the color scheme. Why would I want to change the color scheme? Why are you being such a... As I was saying, unfortunately, there is not a real good way to see how much memory is allocated to your program. But the closest thing I have is the Windows Task Manager. So right now I'm not running my program yet, but I'll keep this. I'll keep this on the screen. Let's put it there. And then when I run the program, go. Don't have to see the terminal. I don't have to see the terminal. Right now you can see that my test program has a working set already of 292 kilobytes. That is just running like an empty program just when I start. So I guess that is standard libraries, and Windows knows what else. So don't worry about that. That's just our baseline, 292k. But when I step into the function, it should kind of allocate another 100 kilobytes. So it should jump up to 392. Let's see. 392. Well, what do you know? So that's good. So that's what I expected. Then when I go out of the function again, it should release that memory. And it doesn't. So it actually does. So the stack memory has been freed. You can't use it anymore. But what this program does, it's a little bit smart. And it says, well, you know, I allocated that 100 kilobyte. I reserved it. I might as well hold on to it for now, so that if this process later down the line kind of needs more memory, I can just reuse the memory that I just freed from the stack. So that's nice, I guess. That's smart. It doesn't really help me with my demo though. So you kind of just have to take my word for it that it actually did release the stack memory. I can show it. I can kind of show it a little bit, so that if I call the function again, the private working set will not increase. So if I say let's call f twice, then the first time I run it, well, it now starts with 296k for some reason, but that's our baseline, 296k. I step into f, it says 396k, so it allocated my 100 kilobytes, and it didn't free anything. That's not true. It did free it, but it holds on to it in case it needs it again. And if I go into F, you see that the working set does not increase. It's still 396. Where if I had like separate functions, so if I make a call of the, if I make a copy of this, call it G, and let's call G from F. Let's say while we're in F, I'm going to call G. Yeah. Oh, still need the breakpoint, but I don't need the second call anymore. Right now, if I run it, I 292, I go into F, 392, it allocates 100k on the stack. But if I go into G, it cannot reuse it because F isn't done yet. Yeah. So now you see that it actually goes to 492. So that's kind of a hint that indeed it just holds on to it and tries to be a bit smart about the memory, which is annoying for this demo, but otherwise it's actually quite a nice thing. Right. So that is the stack memory. That works. But there is a downside to the stack memory. And the downside is it is quite limited. So it can clearly contain 200 kilobytes, but it cannot contain like megabytes of memory. So if I define megabytes instead, and a megabyte is 1,048,576. I mean, we all know that, right? So I should be able to allocate one megabyte of memory, but I doubt the stack is actually 2 megabytes. So let's see what happens if I call this. We start with 292 again. I go into F. That allocates another megabyte. But then I try to go into G, and now things get interesting. Now I get an error. So it paused on exception, as you can see here. So something went wrong. And it went wrong in chickstickmus. And chickstickmus is something I don't have the source code for, so my IDE cannot step into that. But I'm pretty sure I'm pretty sure it stands for check stack, probably MS is Microsoft. Yeah, so it checks the stack to see if we didn't use more of the stack than we actually have, but I did. And this is a Stack Overflow. If this function shows up in the call stack, if something goes wrong here, that's a Stack Overflow. I'm using too much stack memory. So the stack is allocated, I think, by the operating system. It gives me somewhere between 1 and 2 megabytes. I'm using too much of that. Now, this is no good if I want to have a parser that can parse kind of large ini files, right? Because it needs to keep the ini text in memory, it needs tokens, it needs the assignment, and then at a certain point, it also needs the buffer and the entries and all of that at once. So if I have a large ini file, I don't want to be limited by stack size. So that's a problem. And another thing to note is that the stack memory gets allocated at the start of the function. So as soon as you go into the function, all of that memory will be reserved. So even if I have some code put in front of here, let's see if I can show that. Let's create a loop, something that does something for a while. Let's do something silly, something like this. All right, if I put a breakpoint here, what you might expect is, I don't have to put the breakpoint there, I already have one. What you might expect is that as soon as I enter the function, memory doesn't get allocated until I get to this line here, but that's not what happens. So I start again 292K, I go into the function, and immediately it allocates the 1 megabyte, even though we haven't reached that line yet. So anything that gets created on the stack, so that's local variables or arguments, anything that gets created on the stack is created as soon as you call the function. And at the end of it, it also gets released. So the compiler writes code for it, and the way it does that is it needs to know how much of that memory it needs to reserve. That's kind of the way it works. That is why we have to specify here how large the array is. If you don't know that, it's kind of a bit of a pain. Yeah, so what else do I want to say about the stack? I'm thinking if I'm missing something. This is what you get if you go off script. So the heap is kind of all the memory in your computer that is not reserved for the stack. That is a lot more, and you can just ask for it. You can say, okay, this is how much I need. That is virtually unlimited, right? So it's determined by the physical memory in your computer, but even then you have your page file, so you might even have more memory than that, but that should be no problem. You can run out of memory, but it's unlikely to happen, especially for parsing something like an ini file, unless you are dealing with like 16 gigabyte ini files. But I hope you're not. Anyway, so how do we do this if we want to allocate this on the heap? Well, the thing about the heap is that you can ask for that memory and you will get it, but you are responsible for it. It is kind of anything goes in the land of heap memory. You get memory, you do with it whatever you want, and then you release it. That's it. That's all kind of the safeguard you get. So the compiler is not going to help you there. You are responsible. So what that means is that let's here in this function f, let's change this to heap memory. Well, first of all, this is not an array anymore. I'm going to get back a pointer to that memory, and the function you use to allocate memory is malloc. Or malloc, and it needs to know the amount of bytes you want to allocate. So if I want to allocate 1 megabyte, I can just say, oh, give me 1 megabyte. This one is defined in, I believe, stdlib, so it's standard library, and then it's going to allocate that memory for me. Let's see how this works. Okay. So right now 292K. As we had before, we go into the function, and it does go up a little bit. So it does go up by 8 kilobytes. I think that is just the minimal size of a stack for any function. Apparently, it just reserves 2 pages anyway, even if you don't need the full 8K. And because right now I don't have anything, I didn't pass arguments, and the only local variable I have is a pointer to a character. So that buffer pointer, which is 4 bytes. So we don't really need 8K, but that is what it reserves. I didn't get the 1 megabyte yet. That is a call I'm gonna make now. So this is already different than with the stack, right? So with the stack, you immediately get it when you call the function. Here it waits until you actually request it. Right now you can see in the debugger, you can see over here that the buffer is a null pointer. I haven't initialized it yet, but malloc will return a pointer to the new memory. One other thing you notice in the debugger is it also doesn't know how large it is. The only thing the debugger knows is that it's a pointer to a character. And normally the debugger gets its information on size and stuff from the compiler, and the compiler doesn't know, so the debugger doesn't know. So I can open this, but it will only show me the first character. So if I actually want to see more of that in the watch window, I could cast it to an array again. I would not recommend actually trying to watch 1 megabyte in this debugger. It's not really fast. It also doesn't have a memory view, which annoys me to no end. But yeah, what you gonna do? So, but I do want to just show the first couple of bytes that are in this buffer, because that might get important later. So if I cast this to, let's say 100. Okay, so if I open it now, what do we see? Yes. Okay, this is slightly annoying. Okay, these are the first 100 bytes. They are all 0. I was hoping they wouldn't be, because this is a coincidence. What malloc does, it just gets memory from somewhere and doesn't do anything with it. So it leaves whatever value is in there, it leaves it there. Why is my working set not increasing? Something went wrong here. This is not what I expected. It's still at 308K, so it reserved another 8 kilobytes, but nothing more than that. It should have allocated a megabyte of memory. So where did that go? That is so weird. Why? What's wrong? No. This is not, no. No. Why is it not allocate? Why is it not? Why? What if I allocate 100 megabytes? Let's just make it crazy then. This is really, really weird. So it doesn't show up in the private working set, but it does show up in the committed memory. Okay, so get rid of that. Let's try it again. Yeah, so I accidentally stopped the recording, so that was slightly on the stupid side. But we're back in business. So let's look at the commit size. Let's see if that is a better way of looking at this. I'm curious. So I'm gonna make this. I'm gonna put this in G, and in G I'm gonna actually do the stack and see if it's easier to look at the commit size than at the private working set. That took a long time. All right, so yes, back in the function. So right now the commit size is 348K, but when I go into F, it allocates 1 extra megabyte. So it jumps to 1372. And then if I go into the G function, at first, it does nothing to the commit size. That is fine. But then I actually allocate 100 megabytes. So this should jump up by 100 megabytes. And it does jump up by 100 megabytes. So that's good. All right, so don't use the private working set. Use the commit size instead. That's good to know. Yes, so on with what I was saying. So this is good, so you can see that it's actually allocating those 100 megabytes, which is too large for the stack, right? So on the heap, that's no problem. On the stack, that didn't work. But now, if I go out of the function, it won't get cleaned because I'm responsible for freeing it, and I did nothing to free it. So that's actually pretty easy to do. If I want to get rid of it, I will just say free buffer. And that gets rid of it again. So let's call G directly. Don't have to go through F at this point. If I look at the commit size, it's 348. Going to the function G. It was 348. It's allocating 8 kilobytes for the stack. As I said, that's probably just the minimum size of a stack. And now I'm going to allocate 100 megabytes. So there are your 100 megabytes. And if I free it, there you go. It gets rid of it from the commit size. That is nice to see. That is nice to see. I swear when I tried this before, it actually did show up on the private working set. Don't know what happened there. Yeah, so you can see if you call free, then the memory is released again. And that's it basically. However, yeah, but there are a couple things I want to change about this. So first of all, I don't need to look at the size anymore. So one thing I'd like to point out is what you reserve here. It's just in bytes. Yeah, so I can reserve 1 byte if I want. Let's do that. Let's reserve 1 byte. 1 byte reserved. Yeah, but if you look at the debugger, it still shows like, okay, whatever, this entire thing is there in memory. Because to the debugger, this is just a pointer to the start of a character array. And it doesn't know how long it is. It doesn't understand that only the first byte's actually valid, so this one. It happily shows you all the rest that's coming after it, but you should not write to this. This is not your memory. You didn't reserve it. Actually, you shouldn't even read it. That's also not wise to do. But the debugger doesn't care. The debugger doesn't know, basically. Yeah, and that leads to another strange thing. I can reserve 1 byte and put it in an integer, and an integer is in reality it's 4 bytes large. So it of course does need to be a pointer. So this actually compiles and it runs fine. I briefly forgot the key to start there. Whatever. Then I go into the function and then buffer. It's a pointer and it points to an integer, and apparently that integer is this, which is a combination of those first 4 bytes. But still, these things that are now part of that integer, I didn't reserve those. This is wrong. This is never gonna work. If I assign something to that integer, that is bad. So that is something you now have to take care of yourself. You're responsible for making sure everything is correct. So usually what you do in a case like this is if you say, okay, I want to reserve, let's say we want to reserve 100 integers. Then you say, okay, I take 100 and I multiply it by the size of int. And to make this a little bit clearer, I will put it in a variable so that you can see what is actually happening there. Yeah, so here you can see I calculate the size. And the size is 400 because an integer is 4 bytes times 100 integers. So now it actually does what I expect it to do. And that is very convenient and something you need to take care of. And this also works for structs, by the way. So if I have a struct, so let's say that we have our token, which consists of an int start and an int end. Let's ignore the enum right now. Yeah, but so if you have a struct, well, how large is the struct? Well, this is 4 bytes, this is 4 bytes. So that struct should be 8 bytes, right? I can just ask for the size of that struct. So I can say, what is the size of token? And then it should tell me that it's 8 bytes. And it does. 8 bytes 100 times. So now I allocate actually 800 bytes. Of course, I forgot to change the type of the buffer. So it is now reserving 800 bytes and it's treating it as if it's integers, because really, again, what you do with the memory is completely up to you. So if I reserve it based on the fact that structs are, or that tokens are 8 bytes, and then I start using it as ints anyway, the computer doesn't care, the program doesn't care, the operating system doesn't care. That's completely up to you, as long as, first of all, you don't write outside of the bounds of the array, and second of all, you make sure that you free it. Other than that, anything goes. Yeah, so here I free it again. So technically there's nothing wrong with this program. It doesn't do anything that it shouldn't do. It's just a bit weird. It's weird to say I want the size of a token and then actually treat it as an integer. But that's good to keep in mind. And that is very convenient in our case, because we can just ask the size of a struct. That's also why you need to define these things, right? That's why all of these types need to be defined. Because the compiler needs to know the size, otherwise it doesn't know how much memory to allocate for you. So there was another thing I wanted to say. Yes, and in practice, there's another function you can use inside of malloc. There's also one called calloc, and that is the one I want to use. Now I remember again what I was talking about earlier. I was talking about the bytes that it actually reserves, and in the stack it was all zeros, I believe. But here you can see I'm treating this as a buffer. I'm treating the buffer as characters, simply because characters are a single byte. But again, that doesn't really matter. So, but my point is that this buffer contains random garbage. So whatever is left in memory, this is what we can see now, and it happens to be all kinds of weird things. But if you remember in the code that I wrote for the text parser, every time I created an array, I made sure it was zeroed out. I initialized everything to 0, and I want to do that here as well. And there is another function I can use instead of malloc that's called calloc, and that does that. Calloc actually zeroes out the buffer that it allocates for you. Another difference is that it doesn't take the size directly. It takes the number of things you want, yeah, and the size of the thing that you want. Let's also change this to tokens now. Yeah, this does that multiplication for you. So it's pretty much the same thing as malloc. It just does the multiplication for you, and it zeroes out the array for you. Yeah, I don't need this anymore now. This is just convenient. There was one added bonus, and that is that if it does the multiplication, it checks for overflow. So if both of these numbers are really, really large, then it catches that error. So it's slightly safer than malloc, actually. But this is what I'm going to use primarily because it zeroes out the memory. Yeah, let's run it. Let's just run. Everything is going wrong at the moment. Okay, maybe watch this one. Almost done. So at the moment, 356k in our commit size. If I now step over this, I'm allocating 100 tokens. Each token is 8 bytes large, so that's 800 bytes, which will probably not even really show up on the commit size, but maybe it goes to 357. So this was not a very good test, but yeah, you don't even see it because it's in that basically the operating system allocates a memory in chunks of 4 kilobyte. So a page size, the page size is 4 kilobytes. So if I reserve 800 bytes and it's still, did I say 8,000 before? Whatever. If I reserve 800 bytes and it still fits in that 4K, you're not even gonna see it. So this was a stupid test. Stupid test. Let's do 1024 of them. So, and 1024 times 8 byte large would at least be 8 kilobytes. Yeah, so right now 356, so it should increase by 8. It increased by more than 8. Yeah, that's actually a good point. If you allocate memory on the heap, then it allocates exactly what you asked for, plus a little bit more for housekeeping. So it needs to remember somehow how much memory is associated with the pointer it gives to you. And it needs that in case you call free. Now, exactly how it does this is completely dependent on your compiler. Your compiler generates code to do all this for you. But it needs to keep some extra things in memory to be able to free this and know how large that buffer was. And again, the operating system allocates things in pages of 4K. So in this case, I'm saying this line is allocating 8K, which is exactly 2 pages. But if it needs even one byte more, then the operating system needs to allocate 4K. It needs to allocate that complete page just to store the size of this so that we can free it later. All right, I think that is everything you need to know. And now in the tokenizer, I'm just going to replace all of the static arrays with calloc. No, really, that's all. Where do I know how to enter recording. I know the key.